Good morning, everyone. Welcome to Symposium. Today, the first chairman of the session is Professor Andreas Iordanidis. I want to introduce Professor Andreas Iordanidis. Dr. Andreas Iordanidis is a professor at the Department of Mineral Resources and Engineering, University of Western Macedonia and Greece. He is a teaching course on engineering resources, environmental engineering, and medical geology. He has worked at the research and university institution and several European countries, Germany, Netherlands, and United Kingdom, Spain. He has authored 29 publications in journal and 102 in conference. He has 455 citation and index 11 scores. Dr. Andres.
Okay, thank you very much for the
introduction.
So, ladies and gentlemen, good morning. I hope you can hear me, everyone, and you can see me.
Yes, I see and hear.
And I hope the presenters will be all later on, because I think now they are not here. All of them, I mean, some of them they are. So, good morning and merhaba and günaydın and hoş geldiniz to our. I welcome you to our session, our morning session in industrial waste management. I'm going to begin the session with two presentations of mine. And later on, we will have 6 more presentations, and we are going to take. It's going to take 2 hours, from 10 o'clock Turkish time until 12 o'clock. We will the session will last 2 hours. So I'm going to start my first presentation, and I hope everyone is, I mean, the presenters are familiar with the presentations. You can start share screen with the green button down below. So that's what I'm doing now. I will start with my first presentation. And I hope that everyone is watching what I can see in my laptop. So the title of my presentation is the characterization of the coarse fraction of lignite bottom-up samples from Greece. This work was done with the collaboration of 3 universities. My university, which is this, the University of Western Macedonia in northern Greece, the Aristotle University of Thessaloniki, and the Democritus University of Thrace in Xanthi. I would like also to mention my colleagues, Asvesta, Kapageridis, Vasileiadou, Koios, Oikonomidis, and Kantiranis, who all of them collaborated well to do this work. What I want to say now in the beginning is that the 2 presentations, this one and the other one, the next presentation, belong in the same research project. So this presentation will last maybe more in time, but the next presentation will be less in time. So you will see. First, some facts about the lignite exploitation in Greece, I should say. You should know that the share of lignite in the electricity production of Greece now is below 20%, but in the previous years, especially in the 90s, used to be over 80%. So we were a country that used lignite for the energy production, for the electricity. And most of these lignite mines are located in our region, in the region where I live and where is my university, the Western Macedonia region in northern Greece, where we have intensive lignite mining during the last 50 years. However, according to the European law and directions, we have to shift from the lignite to other renewable resources. So lignite is banned, and because it is considered highly polluting, we have to move to other fuels, to renewable energy resources. So lignite burning will stop, according to our law, to our government, will stop at the end of 2023. So talking about the lignite biomass, what is a lignite biomass? Here you can see a schematic plan of a typical coal-fired, lignite-fired power plant. So you can see, in a few words, here is the boiler where we burn, the lignite is burned, and at the bottom of this boiler, at the bottom we collect the so-called biomass. This biomass is generally preserves a high proportion of unburned carbon. So this is what is our samples, the biomass of the lignite-fired power plants. Talking about the lignite biomass in Greece, here you can see a typical lignite-fired power plants in our region. We used to have, not now, a huge amounts of biomass in our regions, in the lignite-fired power plants of Greece. And then especially in our region, approximately 700,000 tons per year. So this biomass, we know that it is used, of course, after careful processing, is used in concrete industry or in geotechnical applications in the globe. But in Greece, unfortunately, it is entirely deposited in abandoned lignite mine sites or in landfills. That's why we treat this lignite biomass as waste, and we don't use it at all. So going down to the scope of my presentation, what we, in this research project, what we try to do, we try to characterize the coarse particles of these biomass fractions in an attempt to evaluate their potential utilization. That's what we did in our work. Going now to the sampling, what we collected 4 biomass samples from 4 lignite power plants, and that is Iordanidis, Kardia, and Meliti. These 3 are situated in our region, in Western Macedonia region, northern Greece, and another sample from the southern Greece, from Peloponnese area, the Megalopolis. So we have 4 power plants in Greece. We collected the biomass samples from these power plants. Of course, this is the processing of the power plants. We took it, we dried these samples, and then we did dry sieving in order to obtain particle size distribution. And in this work, I will focus only on the coarse particles. And when we say coarse particles, we mean particles with a size larger than 1.25 millimeters. So we had this, in this slide, you can see how we did dry sieving. So we collected more fractions, as you can see from these sieves. But, and this is the 4 fractions that we finally took. But in this work, what I'm talking about now, I'm referring only to the coarse fractions. That is the fractions with a size over 1.25 millimeters. So we took these coarse fractions and we conducted many analytical methods on these samples. First, we did the so-called approximate analysis, and that is the measurement of moisture, ash, volatiles, and fixed carbon using this LECO device. And then we also we measured the loss on ignition. We also measured the gross calorific values using this calorimeter, the LECO calorimeter. And we also did thermogravimetry, which is what is thermogravimetry. We heat the sample from room temperature up to 1000 degrees Celsius. And then we measured some very good thermal parameters, which are very good in order to assess the samples, and especially when we have, let's say, solid fuel samples. And these thermal parameters are ignition temperature, maximum rate of weight loss, peak and burnout temperatures, and burnout time. And we also used a stereo microscope to see these particles, these coarse particles, to see the morphology and some characteristics, microscopic characteristics. We also used the scanning electron microscopy, but in this work just the EDS, which is for the chemical analysis, the energy dispersive spectrometer, just to have a chemical analysis of the samples. And we also used an X-ray diffraction device, this device, in order to measure the mineralogical composition of these samples. Going now to the results, you can see here in this slide the particle size analysis. You can see in this we are talking about 4 samples. You can see here the name of the samples: Dimitrios, Kardia, Meliti, and Megalopolis are the name of the samples. Here are the curves of the particle size distribution. Here is the particle size, and here is the cumulative percentage of these samples. You can see that the 3 curves, the particle size curves, are very similar. And this one, which belongs to the Meliti samples, the MLT sample, have some differentiation. Going now to the stereo microscope viewing, you can see here some views we have under stereo microscope. You can see around char particles. You can see like this one. You can see regular char particles like this one, or a semi-fused dust particle, this one, or around again char particle with white inorganic clusters. So we can see many, you can say, char particles in our samples. Going now to the results of the proximate analysis and the LOI and the gross calorific values. Here you can see in this table the samples. We have the 4 samples and the measurements of moisture, ash, volatiles, fixed carbon, LOI, loss on ignition, and gross calorific values. I can focus on these 2 values just to show you something. Here we have a very low value of gross calorific value of the Meliti sample, which is around 700 calories per gram. And here you can see in this sample, Kardia sample, we have a value which is very high, 3,000 calories per gram. I should say that this value could be a value of poor lignite. So we are talking about bottom ash samples, but this value I can say to you that it could be a poor lignite, and this is a typical value of a bottom ash sample. It should be low, the gross calorific value, but here you can see this sample here has a very high value of gross calorific value. In this slide, you can summarize the approximate results and the low and gross calorific values results. So we can say that Meliti sample shows high ash contents, low volatile fixed carbon, low and gross calorific values, which is typical for ash samples, so that it is okay. But these values clearly differ from the other samples, that is the Dimitrios, Kardia, and Megalopolis samples, which have lower ash contents, higher volatile, fixed carbon, low, and gross calorific values. So overall, we can say that it is evident from the approximate analysis and the low and calorific value determinations that the 3 studied samples, this have adequate combustible matter and can be reutilized for energy production. So we can use these samples, we can burn it again, I mean the coarse particles, because they have adequate combustible matter. Here are the results in this slide of the thermogravimetry analysis, the TG, DTG profiles of the 4 samples. You can see 4 diagrams from figures. Actually, here you can see, if we see this diagram, this figure, here is the temperature. So as we heat the sample up to 1000 degrees Celsius, we can see with a blue curve how we have the weight loss, and here is the weight loss, and in this axis we can see the rate of weight loss. So the blue curve is the TG curve, and the Orange one is the DTG curve, the derivative thermogravimetry curve. So in this curve, we can see some clearly some peaks here or here, which all these peaks show something. I will go now to the next slide just to tell you something about these profiles. So in these profiles, we can see three distinctive regions. The first region is below 150 degrees Celsius, which corresponds to the moisture loss. The second region, we'll go back, you can see here or here. And then we have the second region, which is we have the main weight loss, which is actually the combustion itself is due to the oxidation and the removal of volatile matter and then the oxidation of the remaining char. And then we have at high temperatures over 800 degrees Celsius here in this region, you can see in these curves, we have some transformations of the inorganic material, of the inorganic minerals. Watching these curves, we can say that the maximum rate of weight loss in the DTG patterns appears with values up to 2 for the dim sample in this temperature range. But the MLT samples, this reveals rather low maximum rate of weight loss and in a different temperature range. So that is what we see when we are using these profiles, the TG and DTG profiles. Going now to the chemical analysis, the results of the chemical analysis of the EDS, we can see here the 4 samples in this table, and here are the chemical analysis. We found, you can see here calcium, high amounts of calcium, aluminum, silicon, and of course magnesium, sulfur, iron, and lower amounts in some samples of titanium and potassium. You can see this all this in this slide. These 3 samples are composed of elevated contents of calcium, while the MLT sample, the MELIT sample, have higher contents of silicon. That is a small difference, one difference, we say. And then we have magnesium, aluminum, iron, sulfur. The MGL sample from the Megalopolis sample have high sulfur contents because the lignite deposits there have very high sulfur contents. And we also have minor amounts of titanium and potassium. And if we see now in this slide, we can see the mineralogical analysis, the results of the mineralogical analysis. You can see the minerals here and the 4 samples here. So you can see clearly that we have, of course, because we're talking about samples, amorphous material here, quartz and calcite. These are the 3 main minerals, and some other minerals just below in this table. Summarizing the mineralogical results, we can say that we found all these minerals. So we have a great proportion of amorphous material, which could be carbonaceous material, organic material, but also inorganic fused ash material. So this amorphous material could be both carbonaceous and inorganic material. And we also have high amounts of calcite and quartz, these minerals, and some minor amounts in some samples of micas or pyroxene, anhydrite, and other minerals. So going now to the conclusions, and I will finish my first presentation. What we found in our study, we did analytical characterization of the coarse fractions of the 4 lignite bottom mass samples from Greece, and we found that there is an evident differentiation in the Meliti power plant sample comparing to the other bottom mass samples from Agios Dimitrios, Kardia, and Megalopolis. And this is associated with the age and the combustion parameters of the thermoelectric power plants. This is a rather new Meliti power plant, and these other power plants are very old, as I will show you also in my next presentation. So all analytical results, that is proximate, LOI, gross calorific value, the TG, DTG, the EDX, and the XRD analysis witness for the poor combustion in the older power plants. And we can say that the three of the studied samples, the DIM, CAR, and MGL samples, have adequate combustible matter and can be reutilized for energy production. So that is a very nice conclusion, that we can process these samples. We can take the coarse material, the coarse fraction, and we can reburn it to produce energy. So this is my first presentation, and I would like to thank you all for your attention. And if you have any questions, I can answer now, one or two questions. If someone has a question, he can or she can unmute him or herself and ask something. If not, just to save time, I can continue to my second presentation, which will last less, as you can see, because it is a part of the same research project. So I will continue with my next presentation. And this is this. So, as I told you, this is the second presentation. The second work is also a part of the same research project in our university. And this presentation has the title, the efficiency of the lignite-fired power plants as evidenced by bottom-up sample analysis. This work is done again with my colleagues Asvesta, Kapageridis, Vasileiadou, and Koios, and is collaboration of my university, University of Western Macedonia, and the University, Democritus University of Thrace in Xanthi. As I told you, it's a same research project, so these slides are actually the same. So I will pass them. Here you can see the lignite bottom mass, as I told you in the first presentation. Here are the facts about the production of lignite bottom mass in Greece and how we get, and that we don't use it, the bottom mass, the lignite bottom mass. We just throw it away in landfills. It is a waste for us in Greece. And in this presentation, in this work, in my second presentation, the aim of this presentation is that we took representative bottom-up samples from two lignite power plants in our region, in Western Macedonia region. The first one was taken from Kardia power plant, which was founded in 1975, so it is really an old one. And actually now it is closed. Just now, and had a capacity, now it's closed as I told you, of 1,200 megawatts, and the other is the Meliti power plant, which is also situated in our area and was founded in 2003, and this is considered rather new, and has a capacity of 330 megawatts. So we took two samples, bottom-up samples, from these power plants, and we try to see their thermal characteristics in order to evaluate the energy efficiency of the power plants. So we used the analysis, the thermal analysis of the bottom-up samples, and we tried to see if they can tell us something about the energy efficiency of these power plants. The same, again, slides as those in my first presentation. So you can see the materials and methods, analytical methodology. Again, we took the samples, we dried, we did the dry sieving, and then we collected 4 fractions. That's the difference comparing to my first presentations. So you can see that we used 4 particle size groups. This one, you can see here the numbers. So we have 4 particle size groups, and then in these 4 fractions of each sample, Kardia and Meliti samples, we conducted the same analytical methodologies. That is proximate analysis, measurement of moisture, ash, volatiles, and fixed carbon, and then loss on ignition using these devices, the gross calorific values again, of course, thermogravimetry, which is the typical thermal analysis where we measured the thermal parameters. I should focus again on these parameters: ignition temperature, maximum rate of weight loss, peak and burnout temperatures, and burnout time. And we also use stereomicroscope for the microscopic characteristics of these particles. And then now we go to the results. Here you can see the particle size analysis, the particle size distribution. Again, you can see differentiation of, I showed this in my previous presentation. The Meliti sample has a different distribution comparing to the Kardia sample, you can see here. And then some stereo microscope images. Here you can see some macro photographs of the bottom mass aggregates of Meliti sample. And here in this, you can see some macro stereo microscope photographs from Kardia's bottom mass sample. Going to the proximate analysis and the LOI and gross calorific values results, here you can see in this table the samples, the 4 fractions. You can see the 4 fractions in millimeters, 4 fractions of Meliti sample and 4 fractions of Kardia sample. And the measurements, the values of moisture, ash, volatiles, fixed carbon, LOI, and gross calorific values. If we go to this slide, we can see the results of this analysis. So we can say that Meliti samples, which is the younger power plant, Meliti, shows high ash content and low volatile and fixed carbon, LOI, and gross calorific values. And this is clearly different from the Kardia's samples, bottom mass samples, and especially the Coarse fractions, as I told you in my previous presentations, which have in general lower ash content, higher volatile fixed carbon, LOI, and gross calorific values. So it is evident from the proximate analysis and the LOI and gross calorific values that the car samples have adequate, and I'm not talking only about the Coarse samples. I'm talking Coarse fractions. Sorry, I'm also talking of I'm talking for the other fractions and not only the Coarse fractions. So they have adequate combustible matter, and that implies that shows us that there is a problematic combustion in Kardia power plant, which is very old, and it is closed, as I told you now. While the characteristics of the Meliti bottom mass samples indicate a better combustion performance within the Meliti power plant. If we see now the thermogravimetry curves, you can see the Coarse fraction of Meliti sample, and this is the fine fraction of Meliti sample. You can see some small differences in their curves, in the TG curve. The green one is the TG, and the orange one is the DTG curve. So it's the same sample, the Meliti sample, but different fraction, the Coarse fraction and the fine fraction. And we see some differentiations in this curve, in these curves. The same for the Kardia samples, the Coarse fraction and the medium-sized fraction here. So you can see again here some similarities and some differences in the curves, in the TG and DTG curves. And we summarize this. We can see in this slide the table we created based on these curves and the DTG and TG curves, this analysis. So we have in this table the samples, 4 samples, 4 fractions of Meliti samples, and 4 fractions of Kardia samples here in this first column. And here you can see the thermal parameters, the ignition temperature, the burnout temperature, where it starts, the combustion, where it finishes, where we have the maximum rate of weight loss, in which temperature, this is this column, and which is the rate of the maximum rate of weight loss here in this column, and in the last column we can see the total weight loss. All these results are based in these curves. Okay, we took it from the thermogravimetry analysis. And overall, we can say, when we focus on thermogravimetry, that the total weight loss is low, very low, or rather low in mellitus samples and rather high in some fractions of cardiac sample. We can say that the ignition temperature ranges between these temperatures in cardiac samples, and in some we can see higher temperatures in mellitus samples, or there is a small differentiation. And talking about the burnout times, you can see that the cardiac samples displays values between these values you can see here, and the mellitus samples have some other not far but similar values. But talking about the maximum rate of weight loss, we can see that cardiac samples appear with values up to 1.5, you can say, and occurs in the temperature range, this temperature range. On the other hand, mellitus sample reveals a rather low maximum rate of weight loss, and this is a clear differentiation for most of the fractions, except the fine fraction. The fine fraction of mellitus sample shows rather high values, while the Tmax for mellitus samples ranges between these values, which also differs comparing to the cardiac sample. So going to the conclusions, and I will finish now, we can say that in this work, this study, which is, I'm telling you again that it is second part of the same research project. We had several fractions of bottom-mass samples from two Greek lignite-fired power plants. This is Kardia and Meliti power plants, and we analyzed these fractions, and we found definite differences in the characteristics of the bottom-mass between the younger, which is the Meliti, and the older, which is Kardia power plants. And we can say that we found high amounts of unburned carbon, and this is because we have high values of fixed carbon, high values of LOI and weight loss, and this is for the cardiac samples, for the old one, while the mellitus samples reveal low amounts of carbonaceous matter. So overall, the results, what we did in this study, we used the bottom-mass analysis, the thermal analysis actually, thermal characteristics, in order to see if we can say something about the energy efficiency of these power plants. And we can say, I can tell you that we can say that the results imply a problematic combustion and a low energy efficiency for cardiac thermal power plant, which is old, compared to the higher efficiency of mellitus power plant, which is new. So this is my second presentation, and thank you very much for your attention. If you have any question, I stop now, sir, so you can ask anything you want. You can unmute yourself, and you can ask if you want. Has anyone or someone has any questions? So if you have not any question, we can continue to the next presentations and the next presenter. And so I can see from the camera is, I'm sorry for my pronunciation of Turkish names probably and words. So I can see Miss Elif Yavuz. She opens the camera. I have no introduction. Miss Elif, you can introduce yourself, please. I can only say that she will make the presentation of the work with a title Sulfur Dioxide Emission Dispersion from a coal-fired power plant in Çanakkale, Turkey. So, Ms. Yavuz, you can start the presentation. We cannot hear you. At least myself, I cannot hear you. Can you please check? I'm sorry, but myself cannot. If the organizers can hear Miss Elif.
We cannot hear her either.
Okay. Can you check please, Miss Yavuz, again? No, something is wrong. I'm waiting for the help from organizers. Maybe can we do something? I'm asking please the organizers if they can do something, because we cannot hear Miss Elif. No. I don't know if maybe we can shift to the other presentation, to the next presentation, and you can check, Ms. Elif, if you can solve this problem. Okay. Okay. So I hope we will hear in the next presentation, Ms. Elif. We will not have any problems. So if we go to the next presentation, according to the program I have, is from the use of cleaner technology in mining industry from Ceylan. Okay, Eda Ceylan, I can see here. Thank you, Miss Eda Ceylan. I hope I pronounce this right. And Bektas and Ceylan, the use of cleaner technology in mining industry. And Miss Eda, Mrs. Eda Ceylan works as a research assistant at Gebze Technical University at the Department of Environmental Engineering. So, yes. Ms. Eda, you can start your presentation.
Okay. You can see in my slides? No.
Yes. I can hear you and see. Please share
yes.
screen. Okay.
Yes.
Okay.
Okay. Good morning, dear guests, my esteemed teachers and colleagues. Welcome to my presentation. My name is Eda Ceylan. I am working at Gebze Technical University as research assistant with my professor, Dr. Nihal Bektaş. Today, I will present to you my study on the use of cleaner technology in mining industry. It's my content. First, I will talk about importance of mining industry, then process step of mining. In third part of pollution and their source of mining industry. After then, cleaner technology and real application these. Mine is one of mankind's oldest industry. Mines formed in millions of years cannot be replaced when consumed. So planned and obligatory to operate in a rational manner are common values that nature provides to humanity. Mining plays an important role in the countries for means of development and the welfare of people. It meets the raw material needs of many sectors, such as iron and steel production, cement factory. You can see in the slide mining process steps. There are three main steps in mining process. First, searching and preparation of operation. Second one, operation. Third one, mine closure and the monitoring, post-shutdown monitoring. In this slide, you can see the main environmental concern related to mining industry. Generally, dust emission and the noise pollution occur during the exploitation phase, while high-volume waste are generated in the operation section. Greenhouse gas emission and hazardous waste are also generated. In the closure and monitoring phase, pollution monitoring is carried out in underground and surface water and soil in terms of contaminant levels. Mining activities cause significant environmental impact during their operation. Some of the environmental impact continue even when the mine is closed, such as the change to terrain and landscape. Without recultivation, there are still strong erosion and dust emission occurring. West rock dumps still release acid mine drainage into the environment. In this slide, summary of previous slide, production, general potential source of pollution. I want to see your production of acid drainage and mobilization of the metals, mobilization and the release of the natural occurring toxic substance, such as arsenic, which may become air or water pollutant, accidental release of cyanide acid or other introduced materials used in the mining and beneficiation process, exposure of the wildlife, particularly bird, to toxic substance, even when release from the mine site are prevented, generation of the tailing and waste rock, which may produce air and the water pollution. The many mines are located too close to sensitive protected areas. This situation creates an environmental threat for sensitive areas. So it is necessary to prevent mining activities from damaging other natural resources. The goal of sustainable mining is to minimize this damage. In this respect, it's important to compensate or correct the damage caused to the region after the activities for sustainable mining. Clean production is related to 4 parameters, you can see. Sustainable development, pollution prevention, waste minimization, and the pollution control. Green mining means defined as technologies, best practice, and mine process that are implemented as a means to reduce the environmental impact associated with the extraction and the processing of the metals and minerals. The goal of sustainable mining, in summary, minimize this damage. In the mining industry, the concept of the green mining is used to reduce environmental damage in terms of sustainability, high yield, and the high recovery. As a result of the green mining process, it aims to generate less waste and to cause less damage on the ground. With the new technology development, the damage to the ecological environment and waste production during mining process can be minimized. I want to show you real application in mining industry about green mining. In order to realize zero waste in the mining sector, it is necessary to choose technology that generate less waste, benefit from waste, and make waste harmless. For the purpose, the mining companies are reducing their environmental impact with new technologies, so it can significantly reduce the usage of the water and energy at the same time. Now I will give you example. First, control and storage greenhouse gas. Rio Tinto is an example of major mining companies following the green mining trends. The company is testing green technologies at 2 sites in Australia. The first site is New South Wales, is testing methane capturing technologies. Other site located in Victoria in Australia, the company runs a successful carbon dioxide storage facility, which has so far been able to 60,000 metric tons of carbon dioxide storage. Second example of second application, electrification of the mine equipment. In terms of greenhouse gas emission, the Borden mine in Canada has reported 50% reduction in the greenhouse gas emission with the electrification of underground mine equipment. Third one, water management and recycling. Another great step of Borden mine in Canada is the establishment of the water management and recycling program. As a result of 70% of the Barrick Gold sites reuse recycled water, which helps in saving valuable drinking water. Another real application is solvent filtration and replacement. I will give you Barrick Gold Corporation as example about this section. Barrick Gold Corporation is gold and copper mining company with 30 operation areas. It's also a mining giant that is running 140 energy efficiency project, and more than 20% of its electrical energy used in mining operation comes from renewable energy source like solar or wind power. The solvent filtration and replacement of the existing solvent technology can be applied. This technology requires $11,400 annual return of this technology, 9,300 payback period, 14.7 months. The altering a halogenated engine oil with another halogen-free oil, the same market price as its equivalent reduces the amount payback paid by the company, 6,600 in the destruction process. Another application is replacement of the halogenated solvent was carried out with non-hazardous solvent. Normally, the hazardous waste line produced approximately 5.4 tons of waste per year. However, when using non-hazardous solvent in the waste line, produced only 675 kilograms of waste per year. The decomposition of the waste line containing engine oil has resulted in the elimination of approximately 2,025 kilograms of the hazardous waste per year. And last application, intelligent unmanned mining. With the development of the technology, intelligent machine to be used in the underground and the open mining operation have been produced for increased production efficiency and ensure work safety in the mining sectors. At the beginning of the 21st century, Canada, Finland, Sweden, and other development countries made plans for the intelligent and unmanned mining. The primary goal of smart and green mining is to easily adapt equipment to complex technical and geological change encountered during the mining process. In addition, among the goals of the smart and green mining are to reduce the negative environmental impact that occur during operation and to improve the ecological environment. For example, the International Nickel Company of Canada is a typical example of such an automated mine. Mobile device such as scraps, rocks, drills, and underground mining trucks are operated remotely. In other words, workers can operate the equipment directly from the central control room on the surface. When we come up to the end of my presentation, the number of green production technologies that can be applied for the mining industry, which stand out in terms of environmental impact, is increasing day by day. With this waste-free production and environmental-friendly mining approach, the mining industry will become a greener sector than past. It's my references. Thank you for listening.
Okay, thank a lot, Ms. Edda Ceylan. Very nice and interesting presentation, and it is very, because I also work in mineral resources engineering department, so it is actually mining department, and we also conduct research on these aspects, and sustainable and green mining is a very an area of which has a future. I mean, so thank you very much. If someone has any question, he can or she can unmute her or himself and ask. No? So thank you again, Ms. Edda Ceylan. So we can continue to our previous presentation. I mean, with Ms. Okay, I can see here.
Yes. Can you hear me?
Yes.
Okay. Sorry about the problem. Maybe there's a problem at the computer.
Okay, so Ms. Yavuz, you can, I can say again the title of your presentation is sulfur dioxide emission dispersion from a coal-fired power plant in Çanakkale, Turkey. And the work is from Ms. Yavuz, Kuzu, and Saral. You can start. You can make an introduction of yourself if you like.
Yes, I'm Yavuz. I'm a master's student at Yıldız Technical University Environmental Engineering Department, and this is the preliminary work of my master thesis, and it's about sulfur dioxide emission dispersion modeling from a coal-fired power plant in Çanakkale, Turkey, as you say. And this is my outline. First, I will make an introduction to air pollution and SO2 emissions, then continue with location and source properties and model details. Then I will explain my results and compare with other studies and limit values of the regulation. Last, I will make a conclusion, then talk about what will I do in the future studies. And developing urbanization, industrialization, and increase in the world population has made air pollution one of the significant problems, especially in megacities. Air pollution from energy production is an important issue. The increase in the use of fossil fuel has led to an increase in air pollution emissions, and pollution levels have increased. And large amounts of carbon dioxide, sulfur oxides, nitrogen oxides, and particulate matter emitted into the atmosphere during the combustion of fossil fuel. And SO2 has both anthropogenic and natural resources, but it's mainly arise from the power plants which combust coal for power generation. It's a colorless, non-flammable gas at room temperature, and it is one of the 6 classic air pollutants identified by EPA. It can react with water vapor to form sulfuric acid and causes acid rain, destroys forests, ecology, and it also causes corrosion on building materials. And their high concentrations can cause many diseases, such as respiratory illnesses and cardiovascular disease. And it can remain in the atmosphere up to several days and can be transported hundreds of kilometers depending on meteorological factors. And considering their adverse effect on both environment and human health, it's very important to know their levels and predict the behavior of pollutants released into the atmosphere. And for this purpose, various models have been developed to simulate atmospheric dispersion of pollutants by US EPA. There are recommended models such as IRMOD, CTDM+, OCD, and there are also alternative models such as CalPAF and ISCST3. And in this study, I choose to use IRMOD model because it's a recommended steady state model. It's based on Gaussian dispersion, and that determines the direction of the plume going horizontally or vertically. And it's widely used for regulatory purposes with simplicity to use. And it has 2 preprocessors named IRMAD and IRMAP, and they make meteorological and topographic data suitable for IRMOD. And it examines the pollutant concentration over selected model domain up to 50 kilometer area. And it performs well both on simple and complex terrain. That's why I choose to use IRMOD model. And in this study, I choose the Biga thermal power plant as a source. It's in Biga district of Çanakkale, in the northwest side of Turkey, and the province is mostly covered with mountains and hills. It has a semi-moist climate. As you can see close to the source, there are 4 residential areas, Aksaz, Değirmencik, Bekirli, and Kemer, and they all have approximately 600 inhabitants. And Biga is a coal-based thermal power plant with 405 megawatt capacity. And you can see the detailed stack physical parameters in the table below. And there are 2 stacks that have 7 and 4 meter diameters, and both of them have 150 meter high. The first stack has 100 kilogram per hour emission rate and 15 meter per second exit velocity, while the other stack has 202 kilogram per hour emission rate and 33 meter per second exit velocity. And I show the stacks with red color. You can see it in the right picture. And the ground level meteorology station and an air quality monitoring station are available in our study domain. And I show the meteorology station with yellow color, and it's nearly 7 kilometers away from the source stack. And I show the EWMS, air quality monitoring station, with blue color, and it's about 3.5 kilometers away from the source stacks. And in that study, my aim is to calculate stack emission distribution at ground level receptor points. For that purpose, I use IMOD model. I choose the year of 2014 as the calculation period in order to compare with the other studies. And for the IMET preprocessor, I use the surface and radius on the meteorological data. And my domain is 25 kilometer to 25 kilometer with 250 meter grid spacing. And my outputs from the model are hourly, daily, and annual SO2 concentrations. And I obtained the surface meteorological data from the Biga İçtaş meteorology station, and it used as input for the IMET processor, and it includes temperature, cloud cover, wind speed, and wind direction. You can see the observed temperature results on the left figure. There was about 1.5 months of missing data at the station between October 22 and December 1. The annual average value of the temperature data was 289 Kelvin, and the figure on the right shows the windrows diagram for the same year, and the wind speed results varied from 0 to 13 meter per second with an annual average value of 2.63 meter per second. And the dominant wind directions were southeast, northeast, and north-northeast respectively. And IMET preprocessor also requires the radius on the meteorological data for upper level meteorology, and it includes atmospheric pressure, temperature, dew point temperature, wind direction, and wind speed at different altitudes. And I obtained the data from Istanbul radius on the station because it is the closest station to my region. And after running the model, I obtain annual and hourly concentration values and create a contour map with Surfer program. And the figure on the left shows the distribution of annual SO2 concentrations. The annual average concentration is important in determining the long-term effects in the study area. And from this point of view, the highest annual average SO2 concentration was found 0.48 microgram per cubic meter, and the annual average concentration calculated 0.40 microgram per cubic meter at the receptor point, which is EWMS. And the figure on the right shows the distribution of hourly SO2 concentrations, and the highest concentration was found 190 microgram per cubic meter for hourly calculations. That is important because that is the concentration for both, that is the highest possible contamination value under the current conditions. And at receptor, it was found nearly 60 microgram per cubic meter. And as you can see from the both figures, the maximum concentration for both occurred nearly 8 kilometers away from the source stacks in the southeast direction. There are no settlements there, and according to the model results, the highest ground level SO2 concentrations were detected at relatively high altitudes, which is about 250 meters. And daily average SO2 concentrations observed at the EWMS station is shown in the figure. And the data was missing for about 5 weeks between January 10 and February 17. And we can say something went wrong with the measurements towards to the end of the year. And the average of monitored SO2 concentrations were nearly 13 microgram per cubic meter. And a significant increase was observed in the winter months. Probably the increase in the use of coal, especially in winter seasons, can cause such high concentrations in these regions. And the highest value was measured on October 17. And the value is 35.9 microgram per cubic meter. And the reason for increased concentration is thought to be the southwesterly prevailing wind that can carry the emissions from the Çanakkale city center. And if we look at the other studies, Akgüz and Kaynak determined the cumulative effect of 3 operating and 10 proposed coal-fired power plants in the same region using Kalpaf dispersion model, and they calculate for the same year. And they reported that SO2 emissions from thermal power plants operated in the region were transported south and southwest, where the district center is located. And they ran the model for 3 cases and found maximum daily SO2 concentrations estimated at the EWMS, EWMS between 5 and 11 microgram per cubic meter, while we calculated 7.7. These are closest. And according to the model results, the possible daily and annual SO2 ground level values are compared with the limit values of the industrial air pollution control regulation. And considering the 24-hour and hourly average values of the SO2 concentrations calculated during the measurement period, it was observed that they didn't exceed the limit values in the regulation. The limit values are 125 and 250 microgram per cubic meters for 24-hour and 4-hour. And it's predicted that the single potential contribution of the Bigaştaş thermal power plant will be 7.7 microgram per cubic meter for 24-hour and nearly 60 microgram per cubic meter for 1 hour. And considering the modeled and observed SO2 concentrations in 2014, it can be inferred that the calculated pollution levels were below the threshold limits at the EWMS. And to conclude, the SO2 emissions distributions arising from the coal-fired power plant in Çanakkale were estimated with Iordanidis model. The model was executed for maximum hourly, daily, and annual average concentrations, and maximum hourly and annual distribution maps were obtained for the year. The highest estimated model concentration within the study domain was 190 and 0.48 for maximum hourly and annual average concentrations, respectively. And the highest concentrations were observed in the southeast direction of the source and where there are no residential areas. And the annual average concentration was calculated 0.14 microgram per cubic meter at the receptor point at EWMS, while the monitored volume was 13.2 microgram per cubic meter, and the share of the power plant-borne emissions remained quite low. And for future work, I will use the mesoscale weather forecast model to fill the missing meteorological data. I can use weather research and forecast model, WRF model for this, and I will verify the performance of the Iordanidis model with the comparison of other models. Probably I will use the computational fluid dynamics method for the calculation of a single point dispersion at the downwind of the pollutant source, and then compare with both model results with the EWMS results. And since the percentage of missing data in the big H-EWMS and the lack of quality control and quality assurance, they may affect the accuracy of the results. And maybe I will use a differentiation data. Maybe I can expand the study area. And these are what will I do in the future work. And thank you for listening.
Thank you very much, Ms. Elif Yavuz, for your excellent presentation regarding air pollution and sulfur dioxide problems and the application of models in order to monitor these sulfur dioxide problems in your area. This is actually a global problem. That's why in Greece, there is a connection, of course, with the coal-fired power plants. That's why in Europe, or especially in our country, we shift, as I told you earlier, we are shifting from lignite, from coal, to other renewable sources or other fuels. If someone has any question, he can ask, please. If not, I again thank Ms. Elif. You can stop share, please, in order to continue. So we will continue to the next presenter, who is Mr. Mehmet Bilen, who works as a research assistant at Bülent Ecevit University at the Department of Mining Engineering. And the title of his presentation is Evaluation of Coal Mine Wastes in Terms of Spontaneous Combustion Liability and Sulfur Content. Okay, Mr. Mehmet, you can start, please.
Dear Chairman, dear guests, welcome to my presentation. I hope you can hear me, right?
Yes.
Okay. Thank you for this opportunity. I'm going to talk about evolution of coal mine waste in terms of spontaneous combustion liability and sulfur content. We are two researchers from Zonguldak Bülent Ecevit University and the Department of Mining Engineering. And actually we are working as researchers in a mineral processing division of this faculty. And let me go on with my presentation. This is going to be, hold on, let me share my screen. Can you see my slides?
Yes, it's okay, you can start.
Okay. This is going to be layout of my presentation. Next slide. We are going to start with the aim of the study. And then we will go further with introduction, and then I will give brief information about the material and method. Later we will go pass through the results and discussion, and we will finalize it with conclusion and references. Aim of this study is waste characterization, actually waste disposal location for coal mine waste, investigated in terms of waste possible potential of harmful effect for the environment. Coal mine waste and the coal preparation plants waste from TTK, it's a short name of Turkish Hard Coal Association, were under interest and questioned in terms of sulfur content and spontaneous combustion liability. Actually, this study was carried out to understand whether the location of this waste dump is suitable for the disposal or not. In the order of this purpose, waste should be characterized. It was a part of a project, and total of 26 samples were collected 13 of each from the coal preparation plant, and the other 13 is from the production line. And later their corresponding analysis was carried out, and results show that negligible amount of sulfur included in each samples and no spontaneous combustion liability was observed. Let me give brief literature information about this topic. Maybe you are not so familiar with this topic. I will give some brief findings of literature researchers. Coal mine waste, either from the production or from the coal preparation plants, are significant in terms of their spontaneous combustion liability and sulfur content. Sulfur is regarded as the main reason for the acid mine drainage problem. Acid mine drainage problem caused by the oxidation of pyrites and other sulfur bearings in the body of mine waste. Coal mining, according to Dutta et al., Dutta and their colleagues, has a study about the coal mining. Is one of the, and they refer to coal mining as a source of environmental degradation, specifically for the open-cost mining facilities. As many material waste can cause an environmental problem, likewise coal and the associated trace elements can contaminate the soil. That's from also Dutta study. In addition, referring back and forth to the study of Dutta, the authors simply claimed the fact that the position of coal and overburden dumps changed the natural landscape and affects the natural drainage system, and also retards the normal plant growth. Acid mine drainage problem is widely encountered in coal mining areas. Steel mining and processing of coal, the preparation and cleaning can have an accelerating role on exposing to pyrite to water and atmosphere. According to Banerjee, coal mining process increases the rate of formation of acid because of the exposure of iron sulfide minerals to the atmosphere. Not only coal mining areas are affected in terms of acid mine drainage problems, but also the concentration of heavy metals may lead to bioaccumulation, which leads to an increase in the rate of mortality. Although when the environmental effects of coal mining is under interest, most of the time the open pit mining is being considered. Open pit mining is an area where production is realized in open area, and there is other type of mining, it's underground mining. And environmental of coal mining is more of interest in the open mines. Acharya and Karel referred to open pit mining as surface mining, and they explained it as it underpins the shallow mining method to extract coal embedded in the earth by removing overburden covering a coal seam. The same authors above mentioned have explained the fact that surface coal mining accounts for nearly 63% of the total 6,079 total mines in US, which dominates the mine method and the coal mine productivity. Acharya and Carroll have tabulated the corresponding yearly productions underground and surface coal mining activities of US. Surface mining is one of the worst in terms of environment as regards to coal mining. Reasons behind this fact above mentioned is the condenser economic, ecologic, hydrologic, and geomorphic ramifications. Although surface coal mining has much potential in terms of environmental pollution and acid mine drainage, the underground coal mining has also no negligible potential, respectively. Underground production is not always the production as it desired, and some waste is already being produced along with the coal. To be more clear, each production chamber has waste, and not always the aim is realized in terms of low percentage of waste and high percentage of valuable mine. Underground mining problem is not the choice of the location of waste dump, but the waste characterization and the potential to be harmful for the environment. This is already reasonable, as no one desires the coal mine waste dumping area to be polluted in a period of time. In this research, actually, we try to characterize the coal mine waste and coal processing mine waste in terms of their spontaneous combustion liability and sulfur content. Researchers more or less investigated the effect of surface coal mining facilities as regards to environmental perspective, but not many researchers have already focused on underground coal mining potential in this regard. That's why this study is original in terms of this perspective, because underground coal mine wastes should also be characterized, and the place where they are dumped is chosen accordingly. Underground coal mining waste can have high sulfur percentages, and they might also be liable for the spontaneous combustion. That's why in this study, underground coal mining facility of TTK, Turkish Hard Coal Association, was taken into consideration, and their waste samples were collected. As I told you before, a total of 26 samples, 13 by each, either from the production or from the process, collected and analyzed in terms of their tendency to spontaneous combustion and sulfur content. I will give you the results and later on. Let me move on to material and method. This study was conducted with two groups of waste samples. First group of waste samples was originally from the coal mine production, while second group of waste from the coal processing waste. The representative samples of each was collected from each above-mentioned sample location. A total of 26, as I told you, a total of 26 samples was collected with the help of that governmental association staff. Samples were rock samples, and they were questioned in terms of their potential either for the spontaneous combustion and sulfur content. Sulfur content is basically the reason of the acid mine drainage. Right after the collection of the samples, each sample was bagged with the corresponding text. In the order of no possible contamination inclusion, they were tightened up and prepared for the transportation. Characterization of samples were performed in two stages as well. First stage of the analysis is the sulfur content determination. In order to carry out this purpose, representative samples were taken from each sample. In order to carry out the sulfur content determination, we follow the standard as it is seen in the slide. ASTM, American Standard Association, 317775. Initially, samples were crushed and coning and quartering was employed for the samples. Later, samples were ground to 200 mesh and placed on the sample post to determine their sulfur contents. And this sulfur content determination was carried out with the LECO SG132 equipment. And after the calibration of the equipment, each sample was tested in terms of sulfur content. As for the second experimental characterization stage, this is one of the original part of this study actually. Spontaneous combustion liability of each sample was investigated. In order to do so, a spontaneous combustion oven and a sample reactor was employed. This oven is a special oven which composes of air inlet and air out to the sample, and it tries to represent the coal sample atmosphere. As it is known, coals have a tendency to be burned under some specific condition, and resulting in is a fire. This is mostly faced on stock areas of coals, and some accidents were recorded associated with coal mines already. Spontaneous combustion liability characterization is always the primary question for the coals produced, and it should also be questions for the coal mine waste as well. Method of this determination for the spontaneous combustion liability basically covers crossing point temperature, and there are some different index values accordingly. Samples have different ignition points and different initial temperatures to be burnt after by themselves. Spontaneous combustion liability tests were conducted as the method suggested by Feng et al. It's a previous study in 1973. The method at the end results with the index values with which the potential of the liability can be classified. index values above mentioned are FCC index values actually, and these are categorized as classified as low combustion liability, medium combustion liability, and high risk of spontaneous combustion. This cold spontaneous combustion liability tests were carried out with the experimental setup as shown in figure 1. Let me show you the figure 1. This is a new experimental setup in our laboratory. As you see, there are two chromatographs, one of which we are using as an oven for the combustion liability. And we place the sample in a reactor, and then we let the air goes through the sample, and then we have a value of crossing point of coal temperature and the oven temperature. I will show you the results, and then you will understand better about this experiment. Then we have a value that coal is burned, or I mean ignited at some specific degree. And we tried this experimental procedure for the coal mine waste and coal processing waste, just to see if they are liable for the spontaneous combustion or not. As you can guess, spontaneous combustion is also the part of the environmental problems that can cause further environmental problems. Let me show you how we calculate the FCC index in this slide. We have a value of average temperature increase between 110 and 2020. And then we divide it crossing point temperature in Celsius degrees. Then we have a FCC index value, and this FCC index value is classified accordingly in the table tabulated in table 1. If we have a FCC index value between 0 and 5, we have a risk classification of low spontaneous combustion. And if we have a 5 and 10 FCC index value, then we have a risk classification of middle. If we have higher than 10 FCC index value, then we will have a high possible risk of spontaneous combustion. There are some experimental method information here. We put the sample of 35 grams of coal sample and air quantity and oven temperature rise. Let me give you further about the results and discussion. After samples analysis, either in terms of sulfur and spontaneous combustion liability, the results were tabulated. We can see the table 2. Here we see sulfur contents of either the production sample or waste coal processing sample. We donated production samples as prod sample, and we donated processing sample as proj samples, as in the slide, and they are very low, and we understand that there is no possible risk of sulfur content. I can make it faster. I know it takes too much time.
Yes, please, Mr. Bilen, because we have 1 minute only, actually.
Okay, thank you. Let me move on to spontaneous combustion results then. Here are the graphical representation of the spontaneous combustion results, experiment results. You can see there is no crossing point between oven and the sample for each 4 sample. So we can say that there is no spontaneous combustion liability for the test carried out these samples. So we can categorize these samples as no harmful for the in the near future. We can say these samples are not so harmful for the environment in terms of their sulfur content, and they have no possible risk of spontaneous combustion liability. In this study, what we have carried out, we have collected 26 samples, and we characterize them in terms of their sulfur contents and spontaneous combustion liability. And we suggest that coal mine waste, likewise the coal itself, should be characterized in terms of spontaneous combustion liability, and sulfur content is already being researched. These are the main topics that I would like to tell today. This is actually prepared from my full text. So if you have further interest, you can see through the full text of the paper. And if you have any questions, I'm here. I would like to answer them with my pleasure. These are going to be my references. Thank you for your attention and thank you for your understanding.
Okay, thank you, Mr. Mehmet Bilen. Thank you very much for your interesting presentation regarding coal mine waste, and especially this problem of spontaneous combustion, which is really a problem in coal mines. If anyone has any question? Okay, then we can, because we passed the time, we can shift to the next presenter, the next presentation. Thank you again, Mr. Mehmet Bilen. You can stop share, please. So we will continue to the next presenter, who is Professor Dr. Yasar Nuhoglu, who comes from the Yildiz Technical University at the Department of Environmental Engineering. And the title of his presentation is XRF Analysis of Airborne Heavy Metals and Distributions of Environment in Sivas City, Turkey, through dust samples. Mr. Nuhoglu, if you can start.
Hello. Hello.
Okay.
We present XRF analysis, heavy metals. Sesim geliyor mu? Tamam. Heavy metals distribution in Sivas City, Turkey through dust analysis. Bir dakika hemen. Şunu bir küçültebilirsek, evet, şunu bir küçültelim. Şunu. In other words, the effect of the toxic contaminants stem from airborne dust due to urbanization and industrialization in the central and Anatolian city, Sivas, Turkey. Layout, abstracts, materials and methods, research area and sampling methods, sample collision, result and discussion, conclusion. Sivas on the Europe-Turkey-Iran Hikva route is a city with 329,000 people located in the central Anatolia and exposed to the intense air pollution. In the city center, domestic combustion, medium-scale industry, and heat-wise can be contributed to the air pollution. In this research, the accumulation of heavy metals, elements, stem from airborne particulate matters was determined on the ground and plant surface in Sivas city center. Sivas city. Short summary. Airborne particles were investigated in the city center during October 2016 year as a source of pollutants, automobile fuels, gasoline and diesel, coal and fuel oil used in the transportation and domestic combustion were analyzed, and the accumulation on the object in the city was examined. Determining the effect of heavy metals given to atmosphere from fuels, street dust, and the main transportation and metal concentration in the plant tissue were analyzed by XRF technique. The results showed that the main source of the airborne metals are cars and domestic fuels. Materials and method, research area. The city area consists of 115 square kilometers and 359,000 inhabitants. The number of registered vehicles in the traffic, 135,000. It is personal cars, minibus, buses, van pickups, trucks, motorbikes, tractors, and others. The major industry are cement factory, railway car industry, iron and steel factory, far from the city. Street dust samples were taken in January and August 2016 years. Direction in Sivas city. 9 different research points were selected to determine the amount of heavy metals in street dust and tree leaves. The properties of the research areas are below. 1 research point, İnönü Avenue, heavy traffic, crowded population. 3 research point, Mevlana Junction, heavy traffic, crowded population. And control research board, Cumhuriyet University campus. Sample points. Demek şunu küçültür müsün ya? Şu geliyor. Tamam, harika. Tamam. Tamam. Sample collection for the dust, tree and soil samples in the study area was divided into 2 research places as commercial, residential and control areas. The control areas was Sivas Cumhuriyet University campus, which about 6 kilometers away from the Sivas city center. Plant samples. 1, 6, and 8 research point has Scotch pine, Pinus sylvestris. 2, 3, 4 research point has Cyprus Picea orientalis, and 5, 7, and 9 research points has Thuja orientalis. Plant shapes were taken from the tree branch at an average of 2 meters above the ground. All of the material were analyzed by ADXRF spectrometry, except for automobile fuels. Automobile fuels, gasoline and diesel, were analyzed by ICP-MS spectrometry. Resulted discussion to determine the toxic elements caused by the air pollutants from automobile exhaust, domestic and industrial combustion in the city were analyzed, and the effect of those fuels on city dust, plant and human health were investigated. These summary results are given in the table. Heavy metal concentration, pollutant sources, and contaminant sources. Heavy metal, kalsiyum, ferrum, potasyum, alüminyum, titan, sülfür, klorin, stronsiyum, mangan, baryum, vanadyum, zirkonyum, nikel, zinc, krom, kopper, tin kalay değil mi? Tin, toryum, kobalt, kadmiyum, rubidium, lead, osmium, selenium, and others. Plant sources, pollutant sources, gasoline, diesel, automobile, coal, domestic heating, contaminant sources, street dust, soil and tree leaves, as seen in table. Tabloyu geçiyorum da. Tamam. In this study, it was investigated whether 32 metal and metalloids are mixed from the domestic, industrial, and automobile fuels in the atmosphere. The results indicated that the calcium, ferrum, potassium, titanium, sulfur, strontium, and others, thorium, cobalt, cadmium, rubidium, and osmium, originated from the gasoline, diesel, automobile, and coal. Domestic burning. Their vital automobile fuels have no calcium, potassium, titan, sulfur, chlorine, strontium, barium, and others element, and coal have no potassium, aluminium, chlorine elements. The titanium, sulfur, strontium, and the other elements emitted from the only coal burning, and they were mainly derived from anthropogenic activities. Heavy metals such as ferrum, mangan, the others are arised from the gasoline, diesel, and coal more than detection limits. The sulfur, titanium, strontium, barium, zirconium, tin, thorium, rubidium, selenium are only arised from the coal more than detection limits. The titanium, sulfur, strontium, barium, zirconium, tin, thorium, rubidium were primarily originated from the anthropogenic activities. Although chlorine is found in the street dust and plant leaves, its source could not be determined in our research. It is thought that chlorine was originated from an industrial facility, but we didn't make any analysis of this one. Many of those metals, metalloids, have toxic effects on humans, animals, and plants, and the environment, even at low concentration. Therefore, the toxic effects on those metals should be interpreted by comparing them with the finding of previous studies. Some criteria obtained in this research are given below. Table. The toxicity levels of important metals, metalloids, and elements are given table 2. Hazard classes, Russian national classification, European, Dust, Holland, and German national classification. Hic hazardous classes, arsenic, cadmium, mercury, selenium, Pb, Zn, hic hazardous for Russian classification, beryllium, selenium, thallium, and cadmium, hic hazard.
Hocam mikrofonunuzu kapattınız ama.
Yaşar hocam mikrofonunuz kapalı. Mikrofonu açın. Yaşar hocam. Yaşar hocam mikrofonu aç. Mikrofonu.
Sesim geliyor mu? Sesim geldi mi hocam?
Evet, geliyor şu anda.
Tamam. Tamam. The maximum permissible addition of some metal and metalloids in soil and their measured concentration in this research are given in table 4. Heavy metal and metalloids. Maximum permissible addition in environment such as soil. the amount detected in our research as maximum concentration in 1 to 7 research, all of the research points: vanadium, nickel, copper, chromium, arsenic, barium, zinc, cobalt, lead, cadmium, street dust, maximum permissible concentration in street dust, soil, tree leaves, and pollutant source. Vanadium, street dust and soils above the limit. For example, copper, street dust and soil above the limit. Arsenic, street dust and soil above the limit, and other. And the other elements: aluminum, ferrum, titanium, sulfur, strontium, zirconium, thorium, rubidium, manganese. There are no limits in the classification in Russian and German and other. The concentration of street dust, soil, tree leaves, pollutant source. For example, aluminum, gasoline, and diesel automobile exhaust, ferrum, gasoline, diesel, and coal, and others. In table 4, when the source of the heavy metals found in the street dust, soil, and plants are examined, it is seen that barium, titanium, sulfur, strontium, zirconium, thorium, rubidium are emitted from only coal, cadmium, aluminum are emitted from gasoline and diesel, and also vanadium, nickel, copper, chromium, arsenic, zinc, cobalt, and other elements stem from gasoline and diesel. Gasoline, diesel, and coal. The barium, titanium, strontium, thorium, rubidium in airborne particle matters, road dust, and the soil are in the direct proportion of the coal, indicating that domestic combustion for heating is one of the main sources of the two metals. The cadmium and aluminum in airborne particles, road dust, and soils have linear relation with traffic capacity. Cadmium, aluminum in the airborne metals have linear relation with traffic capacity. This indicated that road traffic is one of the main sources of the two metals. The vanadium, nickel, copper, chrome, osmium, zinc, cobalt, lead, ferrum, and mangan are caused by the coal burning and traffic, and other.
Professor, please, you have only 1 minute.
Yes. The average of a cadmium in the Earth crust is 0.2 ppm, but much bigger and more values have also been expressed depending on the different factors. The concentration of cadmium in the tree leaves along this point range from 3 and 215 ppm. Although cadmium heavy metal is below detectable limits in the soil and its presence in the plant tissue show us that this metal is selectively taken by plant tissue. Heavy metal analysis has not been performed on the herbaceous plants, grass, in the measuring station, but cadmium, which accumulates in the tree tissue, which also accumulate in the herbaceous plants. In this way, it will cause bioaccumulation in other living things through nutritional pyramid. The cadmium is in the environment as a result of diesel, gasoline, and tire wear. The maximum permissible addition of the lead is 55 ppm, and our study placed the light concentration range between 16 to 100 ppm. The lead values in the almost all locations are greater than the corresponding values. Liat is not dust in most originated from the coal and automobile fuels. The important amount of liat, which is found in soil and street dust, was derived from coal and similar amount caused by the automobile fuels. The zinc concentration in the street dust, soil and tree leaves are 450, 89, and 101 ppm respectively. Most location show greater values than average heavy metals value of the world soil permissible concentration. Roadside dust in urban areas is an indicator of heavy metal contamination from atmospheric accumulation. As typical pollutants in the urban environment, metal in street dust are useful indicators of environmental pollution. In addition, metals in street dust can easily pass into the human body through inhalation, ingestion, skin contact, and nutritional pyramid, and can easily accumulate in the fatty tissues, circulatory system because of their toxicity, non-biodegradability özelliği. For this reason, more concentration has been raised about the problem of street dust contamination with metals in recent years, and a lot of research has been done all over the world among detected two heavy metals in terms of toxicity. Arsenic, zinc, cadmium, selenium, Pb are very toxic. Cobalt, nickel, chrome, and copper are moderately toxic, and strontium, barium, vanadium, manganese, cobalt, tin are less toxic metals in living things. Conclusion yukarıda var zaten. Tamam. Thank you very much.
Okay, Professor Nuhoglu, thank you very much for your interesting presentation. And it is very difficult to really to find the source of potential toxic elements and heavy metals, especially in the dust samples, in the airborne samples. So it was really very interesting, your presentation. But because we don't have much time, I think we could not have time for questions. So we will shift to the next presenter. So you can stop share. Professor Nuhoglu, you can stop share, please. And we will shift to the next presenter, who is Professor Arapoglu from Eskişehir Osman Gazi University at the Department of Industrial Engineering. And the title of his presentation is Productivity Improvement at Motor Vehicle Inspection Station by using Taguchi approach.
Thank you.
Professor Nuhoglu, can stop share, please, in order to proceed.
Yes, please. Thank you, all of you.
Okay.
Okay.
Just put the stop share button.
Just.
Okay.
Okay. Okay, can you hear me?
Yes, okay.
Okay. Hello, everybody. My name is Aykut Arapoğlu from Eskişehir Osman Gazi University from Industrial Engineering Department. And I'll talk about the production improvement at the motor vehicle inspection station in Eskişehir by using the Taguchi approach. This will be because I'm an industrial engineer. This is going to be a more technical presentation, and I'll talk about the vehicle inspection station, how to improve the productivity at the station. The outline of the talk, I'll start with the introduction, a short introduction, and I'll talk about some literature review related with the talk. And then I'll talk about the motor vehicle inspection station, the current workflow, how work is done on the floor. Next, I'll talk about the stages of the vehicle inspection and the evaluation and reporting of the results. Then I'll talk about the current status and some observations made at the station. And then I propose a arena simulation model which simulates the operations at the station. And we will analyze the results by using a design of experiment and Taguchi method. And at the end, I'll present the results and conclusion. At the introduction, many different type of size of vehicles need to be inspected at the station. And sometimes we face with long waiting times and long waiting duration, and long lines are reserved. The current company is the only company authorized in Turkey for vehicle inspection. They cover the old 81 cities of the Turkey by 205 e-mobile and 76 mobile stations distributed around the whole country. The aim of the study is to improve the efficiency at the inspection station by using simulation and Taguchi method of design of experiment at the same time. The output of the simulation will be used in the design of experiment part of the study. And the location we selected is the Central Vehicle Inspection Station located in Eskişehir, a city in the central Anatolia. This is some literature review. I took some literature review that deals with inspection stations and simulation studies at the same time. The first one is from Saudi Arabia in Riyadh. They try to increase the effectiveness of the vehicle inspection station. The second one is from a Turkish people. They use Monte Carlo simulation by capital budgeting process. In the last one, they try to find possible solutions and alternatives to increase the efficiency and effectiveness of the vehicle inspection stations. Of course, there are more literature in this area. Let's go back to the station, and I'll give more information about the station. This station operates on 100% fully appointment based. So you need to make an appointment before going there, and each appointment is separated by 15 minutes. You have 15 minutes between appointments. There are 5 parallel inspection lines. The first 3 lines are reserved for the sedan or regular vehicles, and the last 2 lines are reserved for heavy vehicles like trucks and buses and so on. There are 2 exhaust emission testing areas, but we are not dealing with this part of the station. We will concentrate on the parallel lines. The number of technicians changes from time to time, from 8 to 16, and depending on the latest regulations like imposed by the government, which says that short like short working times are allowed. These are the times of works or shifts, and the inspection process itself consists of 5 stages. Now, the current workflow works like this. You need to make an appointment at the beginning. You need to be there for location and the time of the appointment. Upon entry, you take the queue number from the kiosk at the entrance. When line is okay, you check for fine. If you have any fine, taxes, and you pay for the inspection fee. And then you start waiting for calls. The calls are important because they call you by name for inspection when the time comes. And then you proceed to the line designated to you. Then you get ready for the head of the line. You go to the head of the line. First, a pre-check, a visual pre-check is done, and then the car is taken into the premises and the building, and 3 stages of inspections are made. At the end, after the checks, a report giving you the result of the check or inspection is given to you. This is the pre-check, pre-inspection checks. First of all, they check for the possible unpaid fine, tax, insurance. They check for validity of the current exhaust emission test, and also some simple checks before inspection. Checks for gas leaks, if the vehicle works with LPG, checks for mandatory equipments, emergency kits, and so on. In the first stage of the inspection, vehicle identification, control of the registration information is done, and the braking system is checked by using special equipment. And then the car is taken to the next stage. In the second stage, the check points are like hood logs, hoses under hood, fluid levels, battery and connections, and so on. And also some in-control vehicles, in-vehicle controls are also made. The visibility check, mileage, and the windshield water spray are also checked. Lights, reflectors, electrical equipment, lighting systems, and headlight adjustments are checked in the second stage. In the third stage, the vehicle is lifted, and the technician goes below the car and it checks for oil and fuel leaks, exhaust and front and rear suspension systems, corrosion damage, any leakage, or vehicle load carrier system are also checked. These are the 3 main stages of inspection done. After the inspection is completed, a report is issued. If there is no flow or light flows or minor flows, it's passed. The car is passed okay. If there are several flows, then you need to re-inspect within a month. The current status and observations. 100% this inspection station works on 100% appointment based from the 8 a.m. 4 p.m. With 15 minutes intervals. This means every 15 minutes a car is given an appointment. We assume 5 inspection appointments for each appointment slot. This number can change. The first 3 lines are reserved for sedans. Yes. After the pre-installation process is completed, the waiting starts according to the sequence number taken from the kiosk at the entrance. Long queues sometimes are observed time to time, and the number of technicians varies time to time. Admission to inspection done is by calls, regular time intervals, and interval between calls. Admission to inspection is done by calls by name, and this is done by regular time intervals between calls. So every 10 minutes or every 5 minutes, cars or vehicles are called for inspection. The number of technicians and call frequency, this is called call frequency, time between calls. These are the the service rate at the station. These are some assumptions related with the simulation study. We assume only 3 parallel lines. Every vehicle show up on time. The queue discipline is important. Of course, the FIFO queue discipline means that the order, when there is a need, the order of service when there is a queue. FIFO means first in, first out, and LIFO means last in, first out. We also consider the number of vehicles with LPGs to be 38% because they require one more check for the LPG leakage. Every vehicle is inspected by a single technician. These are the assumptions of the simulation models. We make no distinction between type, model, brand, or age of vehicles. We consider all vehicles the same, but there are some variations related with the inspection times. A fixed number of vehicles are called at each call. So every 5 minutes, for example, 4 vehicles are called. For example, all employees are available during the day, no break. First car admission at the morning at 8 o'clock in the morning, and last admission is 4:30 p.m. We are not interested with the final decisions. We are not interested with if the vehicle pass or fail. We are just interested in how they wait and how the process is done. We observe 3 main performance measures: the mean flow of time, throughput, and the mean waiting time. Mean flow of time means the total time the car spends in the system. Time out minus time in. Throughput is the percentage of the cars that are served satisfactorily during the service. The mean waiting time is the actual waiting time of the cars just in the station, like just wait for the call. We use the ARENA model, ARENA software. It's a discrete event simulation software developed in 2000 and mainly used in production and service systems. And the version 16 is the one we are using. In the simulation model, the main thing is the times for processes. Here on the left, you see the different processes. If I can, different processes, and these are called activities, and each activity has a processing time distribution given to them. We assume a triangular distribution, meaning that the first, for example, the first entry, the first parameter of the triangular distribution means this is the least amount of time this activity can be done. Second parameter refers to the mode of the distribution, and the third parameter refers to the pessimistic estimation, or how the longest time that can be observed. Since we are not expert on this, we asked on the technicians as the experts' opinion, and we got these numbers from the technicians actually performing the tests. And the triangular distribution is the proposed distribution for expert opinion in simulation. This is the view of the RNA model. You see, this is the vehicle entry, and goes 3 parallel lines, and they leave at the end. Here, the Taguchi method. I'll talk about the Taguchi method. This is one of the powerful problem-solving techniques for improving the process performance, yield, and productivity. It was first proposed by the Japanese engineer Taguchi after World War II. I mean, the focus of the Taguchi method is to minimize the processing variation. The variation in the process is something that we do not want to see. And another aspect of the Taguchi method, it reduces the number of experiments. If you need to, it reduces the number of experiments needed to perform significantly. The aim of the Taguchi method is to reach a robust design, which means to optimize the settings of control factors to optimize the response with minimum variation. Let's say the control factors, I'll talk about next, about control factors and noise factors. Control factors are the factors that we can control them. In simulation, we can give those parameters to the simulation model, and the model works works by using the factors, control factors given by us. We have control on these factors. For example, vehicle admission rate, vehicle calling frequency, number of technicians used, and queuing discipline are all the control factors that we can control. And also there are other factors that are called noise factors that we do not have control on these factors, and they are because they are either too difficult or too expensive. So for example, type, model, or age of the vehicle. So there are some variations in the duration of the inspection because of the age of the vehicle. And also there are some variations due to the technician to technician variation. A technician can be an experienced technician, can perform the inspection in a shorter time, and so on. So these are the noise factors, and that we don't have any control on these factors. And the response variable is the throughput rate, and the Taguchi method converts this throughput rate into a signal to noise ratio. This is actually a ratio obtained by a formulation. And also the aim of the Taguchi method is to determine the control factor settings that best reduce the effect of noise factors. Here we are looking for optimal control factor settings that reduce the noise. We try to reduce the noise.
I'm sorry, Professor Arapoglou, you have to finish. Just 1 minute, please. Because
it's... Okay. There are 4 control factors. The first control factor, vehicle admission rate, we denote it by A. The second control factor is the vehicle calling frequency. This is how frequently we call the vehicles. The third one is the number of technicians, also we can control it. The queue discipline also another control factor. We assume no interaction between factors in this statistical sense. This is the levels that we used for the vehicle admission rate. The low level, there are 4 vehicles admitted per 15 minutes, in high level 8. Vehicle calling frequency in the low level every 5 minutes, and the high level is every 10 minutes. A number of technicians in 2 levels, and queuing discipline in 2 levels. So if you look at, if you perform the analysis by using every combination, you need to make like 2 times 2 times 2 times 2, and 16 separate experiments are needed. However, in the Taguchi orthogonal array, we don't need 16, we just need 8 experiments. The Taguchi experimental setup is done so that the 8 experiments are performed by taking the most information from the experiments. And we make 5 replications on each. These are the observations that we took. These are the averages of 5 observations. There, you see, we only take 8 observations instead of 16. This is the signal-to-noise ratio, how it's computed, and this is the values of the signal-to-noise ratio computed by the Minitab. In the low level, the higher the signal-to-noise ratio, the more robust the system is. From here, we see that level 1 for the first factor, level 2 for the second and third factors, and level 1 on the fourth factor are selected as the output of the Taguchi method. This is the plot of the factors. You see the first, the higher, we always check, we always see the highest factors. And for a robust design, it is recommended that the main factors levels should be set as A1, B2, C2, and D2, which means that every vehicle admission rate should be like 4 vehicles should be admitted every 15 minutes. Vehicle calling frequency should be 10 minutes. Every 10 minutes, vehicles should be called. The number of technicians, like 16 technicians should be used. And the queuing discipline, FIFO queue discipline is recommended. As a similar analysis could be performed for mean flow time and mean delay in queue by using the same analysis. And this is the, I guess, this is the end of the presentation. Thank you for listening, and I will be happy to answer the questions.
Okay, we thank a lot, Professor Arapoglou, for his interesting presentation. And we saw from the point of an industrial engineer how important is to improve a motor vehicle inspection system. But I think we don't have, we passed the time, and probably we'll go through the other afternoon session if we continue like this. So I'm sorry, we don't have time for questions. We'll just shift to the final presentation, to the final presenter. So thanks again, Professor Arapoglou. We can go now to, I can see the presentation, the title of the last presentation is Sustainable Approach for Alternative Raw Material Resources, Reuse of Phosphogypsum. I think that the first author is not here, and the presenter will be Suna Ertuğ. Am I right?
No, actually, I am Didem Dirmanbaşı. I'm going to present the study.
Yes.
Okay, so Didem Bai?
Yes,
okay.
I'm Didem.
So you can start your presentations, please.
Just a minute. I'm trying to share my screen.
Okay.
Just a minute.
You can also open your camera if you...
Sorry, I have bad internet connection. I can only use audio.
Okay, never mind. Okay.
Just a minute.
I think we have a small problem here. So Didempai is trying again to connect, and I hope now successfully we'll make the presentation.
Hello, I'm returned. Could you mind to me? Yes, okay, thank you.
Okay.
Okay. Hello, dear all. I'm Didem. I'm going to present my study about a sustainable approach for alternative raw material resource reuse of phosphogypsum, focusing on marking a process flow diagram, which is used dealing with waste of phosphogypsum and production for a useful product is the aim of this study. This study was carried out with in the scope of the 2244 Industrial PhD Fellowship Program partnership with Ankara University Chemical Engineering Department and Toros Agri Research and Development Center. Toros Agri has a phosphogypsum stack in 2 different facility area, and total amount is 25 million tons. Ankara University support the project with the students' knowledge and experiments. Toros, the fertilizer producer and one of the largest manufacturers with 3 production facilities in Turkey. Annual production capacities are on the slide. Toros Research and Development Center serves in 3 factories, and it's located in Mersin. Toros is the Tekfen holding company, and Tekfen Agri Industry Group is more than just fertilizer production. For example, terminal service, free zone service, field seed, seedling, fruit production, and etc. What's included in this presentation? First of all, general information about phosphogypsum, then how to perform my experimental studies and their results. Finally, I'm going to summarize all of this study. Now I'm going to start giving an information about phosphogypsum. Its basic formula is calcium sulfate dehydride as like gypsum. It's a solid industrial waste containing impurities. The impurities composition in the PG differs depending on source of phosphate rock. 250 million tons PG emerge every year in the world, and it's over 4 million tons today as a bulk. A large amount of waste PG is produced during the phosphoric acid production by wet process, and it's based on composition of phosphate rock with sulfuric acid as shown in the figure 1. Recycling of the PG is limited due to high content of impurities. In the world, phosphoric acid is produced when wet and dry process. In wet process, you can use direct phosphate rock and obtain high volume production, but low purity. In dry process, you can use elemental phosphor and get more pure product, but this process both expensive and product volume is small. For this reason, 90% of producers prefer wet process production. In wet process, to produce 1 ton of phosphoric acid must produce 5 tons of PG. In this reason, such large amount of PG stocks exist today. In April 2014, the United Nations Economic Commission for Europe, it should be considered as a secondary resource rather than as a waste due to the valuable substance in the PG. As shown on the slide, you are seeing the European West hierarchy. Reusing is important step for phosphogypsum. On the slide, you are seeing uses of PG as a secondary source. Around the world, the top 4 uses are agriculture, used for road construction as a building material, and soil stabilizer. In this section, I'm going to tell my experimental study. The phosphogypsum used in this study was obtained from Toros Agri Merton field, as you can see on the slide, taken from stock 1. A sample was dried at 105 Celsius for 24 hours. We used 2 different processes to produce sodium sulfate. In process 1, PG is reacted with sodium hydroxide for 3 hours. End of the reaction, solid and liquid phase are separated. Liquid phase is characterized as a sodium sulfate. By process 2, PG is reacted with sodium carbonate for 30 minutes. End of the reaction, solid and liquid phase are separated. Liquid phase is characterized as a sodium sulfate, which is our main product. The difference between process 1 and process 2, we use sodium carbonate in process 2 instead of sodium hydroxide. Also, reaction time is lower. The output obtained as a result of the production process, we analyze and characterize by instrument devices such as ICP, FDR, XRD. In this slide, we are seeing FDR results of commercial sodium sulfate and our process 1 product. The use of PG are smaller than 850 micrometers. 2 chemical peaks are almost identical, and the peaks from impurities were marked. In there, the future results of sodium sulfate by process 2 and commercial sodium sulfate, the used PG are smaller than 32 micrometers. 3 chemical peaks were almost identical. It's the sulfate group's peaks. It's the XRD results for sodium sulfate by process 2. The sodium sulfite is produced is 75% pure. It's the demonstrated heavy metal concentration of PG, commercial and produced sodium sulfite. Heavy metals mobility in PG wasn't the sodium sulfate side. Due to project confidential, all the results are not allowed to be shown yet. If the sum of the whole study, phosphogypsum is byproduct of wet process phosphoric acid production and still an unresolved problem. Only 50% of PG is used as a secondary raw material, rest in disposed in open type stacks. With the proposed process, both waste recycling is provided and valuable industrial raw materials can be produced. 75% purity sodium sulfate is produced. Higher purity products can be obtained if the impurities can be removed by applying biological, chemical, or physical pretreatment to phosphogypsum. We would like to thank to Toros Agri and Tübitag for their financial support, and thank you for listening.
Okay, thank you very much, Mrs. Dem, and thank you for keeping the time and being very short. It was really an excellent presentation, and I think it is very interesting to see how we can reutilize this byproduct, this waste product, phosphogypsum, and in the frame of circular economy, I think it is very, very important. I can see that we passed the time half an hour after 12 o'clock Turkish time, so I think we don't have time for questions. So at this moment, I would just like to thank first all the presenters for their excellent work, their excellent presentations, and then all the participants at this session. So I wish you all a good day, and in Turkish, güle güle. Thank you.
Thank you, Mr. Andreas. The session is over. Thank you for attention. Bye-bye.